All right, let's get into units of measure or solution concentrations. All right, this is just a way to describe its components. In terms of units of measure, right? So we have different concentration units we have to worry about. The first one would be percent by mass. And percent by mass would be basically equal to the mass of the solute divided by the mass of the solution times 100. So if you had something that was, 37% HCl by mass, right, that would be, kind of using as a conversion, right, would be 37 grams of HCl for every 100 grams of the solution that is contained in. So, as an example, we could say, if 13.2 grams of sodium chloride are dissolved basically into a solution containing 25 grams of methanol and 150 grams H2O. What is the percent sodium chloride by mass in solution? So we have that notion of, what we're looking for, mass percent. So that means that we would be looking for the percent sodium chloride, which would be really the mass of the sodium chloride NaCl over the mass of the solution. And the solution mass, right, would just be equal to all of the parts. So that would be, the mass of the sodium chloride plus the mass of the methanol, right, and plus the final mass, the mass of the H2O. So we have all those pieces, right? We know the mass of our sodium chloride, we know the mass of our methanol, and we know the mass of our H2O. So we can put this all together and solve for that percent sodium chloride. So we would have our 13.2 grams divided by 13.2 plus 25 plus 150 times 100. So those are those three components that we have, right? We have the sodium chloride, we have the methanol, and we have the H2O. And that equals 7.01% sodium chloride by mass in that solution. So that's an example of mass percent. Another way we can describe solutions would be by volume percent. And so that would be very similar in terms of now just in terms of volume, with volume of the solute divided by the volume of the solution times 100. So again, it's kind of like a conversion feature for us, that if we have 15% ethanol by volume, that would be the same as saying, well, I have 15 milliliters of my ethanol for every 100 milliliters of solution. And so really these are, these are conversion features for us. Let's look at an example of this. How would you prepare 250 milliliters of a solution that is 30% toluene by volume in chloroform? So here is this expression, right? We see that 30%, so we know that we have this solution. It's 30% by volume. So we actually already know the percentage, and now we're trying to figure out how we can actually make it. So we know it's 30% by volume, toluene. So that tells us that, okay, that's really telling us a conversion feature, that we would have, 30 milliliters of the toluene for every 100 milliliters of solution. We also know how much of the solution we have, right? We know the volume. It is 250 milliliters. So we can use this really just as a simple, conversion tool for us, that if we look at where we want to go, we want to know the volume of the toluene, so we can know how much to actually measure out in terms of creating the solution. Our measurement is 250 milliliters of solution. Remember, that's where we like to begin. And so what we need is a conversion between those two, and that's where the 30% is going to come into play. To allow me to make the connection between those two. So that's the game plan. We're going to take the volume, we're going to apply the conversion feature, right? And so that's what we see in the middle. That's our conversion. Again, remember, conversions often highlighted by the fact that they have a numerator and a denominator. And so we start with that measurement of the solution, 250 milliliters. We're now going to apply that conversion that we see in the middle. And we're going to set it up so that the volume and what the volume is describing cancel out. So we want to have the 100 milliliters of solution in the denominator so that the volume of that solution is canceling. And now we know that we would need to add 75 milliliters of toluene. Would be needed. So to prepare, 250 milliliters of 30% toluene in chloroform. Again, this is by volume. One would measure 75 milliliters of toluene and then dilute with the remainder, right, the 175 milliliters of chloroform. And so that is our answer. So that's how we can use these, specifically volume percent, but we can do the same thing with mass percent, is using it as, a conversion feature for us. The third one that we will use a lot is molarity. And this is moles of solute per liter of solution. And it's given as capital M. And like I said, we're going to be using this basically a lot. So this is really, if you think about it, an access to moles, and that's why we tend to use it so much. And we can do the same thing for the mass percent and volume percent, but we'd have to do a couple extra steps to get to a mole value. Using those conversions. With molarity, it's really direct, right? Because it's really just describing how many moles of the solute are in every liter of solution. So let's do an example of this. Let's calculate the molarity of a solution that was prepared by dissolving 50 grams of ferric chloride into 450 milliliters of aqueous solution. So that's our question. We want to know what the molarity is of this solution. So that's where we're going towards. Right, molarity here would be moles of the iron or the ferric chloride per liter of solution. And we don't know the moles of the ferric chloride, but we actually do know the volume of the solution, which is the 450 milliliters. So we just need to basically figure out moles, right? Almost like, doing a two-step here. We need to get to moles first, and then we can put that together to solve for the molarity. We have access to moles from the 50 grams of the ferric chloride. So we can easily get to moles, then divide by that volume of solution to arrive at a molarity value. So we would start with the mass and divide by the molar mass of 162.5 grams per mole. And so we have 0.310 moles of our ferric chloride as a result of that conversion from mass into moles. And now we can go to the second step, which is just plugging it into the molarity. So the molarity of that ferric chloride solution would be equal to the 0.310 moles of ferric chloride, right over the 0.450 liters of solution to give us a molarity of 0.685 molar. So that's how we can calculate molarity for a particular solution, right? Really, that moles of solute over then the total volume of solution. Often we do dilutions of what we call stock solutions, and we've already talked about stock solutions earlier. Stock solutions are, basically very concentrated solutions. And since they're concentrated, that means that we can actually dilute them. And so what we can do is we can dilute that to then basically provide, a plethora of concentrations, right? We can produce, another word would be a multitude of concentrations, right? Because it's very concentrated. So it's easier for us to, as scientists, to keep very concentrated solutions in the lab. Takes up less space, and then whenever we're using, or need rather a solution for a given reaction or workup or what have you, we can just go to the stock solution, dilute it to the proper degree to give us the solution concentration we want for our experiment, and then we can use it for our experiment. So often we do dilutions of these stock solutions. The constant in a dilution is moles of solute. So that's an important feature, right? And we have an equation that can really describe that in terms of M1V1 equals M2V2, where here we have on the left side a molarity and a volume, and this would be, conditions 1. Say, the stock, but, it doesn't have to be that way. And then on the right side, we have our volume and our molarity for basically conditions 2, which you could call the dilute. So it's just a way for you to interconvert between each one. And if we think about the units here, right, we have moles per liter, times liters, right? Because that's M1V1, right? Molarity is moles per liter, and volume is in liters. And we can say the same thing on the other side. And at the end of the day, right, once those cancel out, right, we're left with moles is equal to moles. And that is our solute constant. So we need to understand how to do dilutions as well. Let's do an example of a dilution. So here's our question. An experiment calls for 3 liters of 0.5 molar calcium chloride solution. So that's what I need for my experiment. How would you prepare the solution from a 10 molar calcium chloride stock solution? So if I look at some of this information that I'm given, right, I have this, volume. And I have a molarity. Both of them, with regards to calcium chloride. And so we could call this, right, it doesn't really matter, condition 1 or condition 2. I'm just going to say this is, conditions 1. And then we have, on the other side of the game, right, we have this 10 molar calcium chloride stock solution. So we have, 10.0 molar for our molarity, again, of the calcium chloride. But what we don't know is the volume for that calcium chloride. So these are, again, talking about the same molecule, so this is really just a dilution. And so over here we would have then our conditions 2. So the game plan would be, if I can, figure out the volume of the stock solution that is required, just, I can dilute that to the 3 liters. Basically with water. So the idea here is that we want to use, M1V1 equals M2V2 to figure out the relationship. What's equal on both sides is that the moles of the calcium chloride is equal to the moles of the calcium chloride. And so I'm just trying to relate the volume molarity issue, the concentration volume issue. So if I start to plug them in, I have my molarity of 0.50 molar. I have my volume of 3 liters. I have my 10 molar for the stock solution. And what I'm trying to solve for here is V2. And so if I solve, I get a V2 equal to 0.150 liters. So basically, you measure out 0.150 liters of stock solution, and then dilute up to 3 liters with water. Right, so that would be basically the volume of water addition would just be the difference of the two, right, or 2.85 liters. So that is looking at a dilution, how we can go from a concentration of one solution and then generate a concentration in a different solution. And so again, we usually use stock solutions for this protocol. So we can, it's harder to get more concentrated, right? It's way easier to take something that's already very concentrated and then just add as much solvent as you need for whatever your requirements are for that particular experiment. A tougher example would be one where we could, incorporate, more than one of these conversions. From above. So let's look at this example. We have the question asks us how many milliliters of concentrated HCl. Concentrated HCl has a density equal to 1.18 grams per milliliter. The solution is percent HCl by mass is 36%. And the molar mass for HCl is equal to 36.5 grams per mole. So how many milliliters of concentrated HCl have to be mixed with water to produce 250 milliliters of 2.00 molar HCl. It's aqueous. So there's our question. We have how many milliliters of concentrated HCl is what we're looking for. We have some properties there. Notice all those properties have 2 units, one in the numerator, one in the denominator. So more than likely those are conversions. But how many milliliters of this concentrated HCl have to be mixed? in order to produce this solution at the bottom, 250 milliliters of 2 molar HCl. So let's start with where we want to go. We're looking at how many milliliters of this concentrated HCl. So that's really kind of our end game here. And we have two different solutions. One is concentrated, and that's really our stock solution. We have a bunch of different values here in terms of density, percent HCl by mass, and HCl. But we're going to find that these are all, conversions, right? With this idea of, a unit over a unit. And then if we keep going down, we're trying to figure out how much of that concentrated we need to mix with an actual solution. So we know that, what we actually want to make, which really is kind of the beginning piece. Meaning, here is our measurement. And this, well, in terms of the 2 molar, this is really a now dilute solution. So we're really looking at a dilution, right? This is a dilution example. So what does that mean? That means our moles of HCl is constant. So that's really going to be probably the fulcrum between one unit and another, meaning that we have this 250 milliliters, and that is our measurement. That's where we should start. And we're trying to figure out this concentrated HCl, but often it's, nice to look at it in a retrosynthetic way. Meaning, what unit would I want the concentrated HCl to be in order to finally convert into milliliters of HCl? And if we look above, that unit, or conversion rather, that carries this grams per or carries this milliliter value is really the density, right? We look at the density, it's 1.18 grams per milliliter. So if I could get into grams of this concentrated HCl, I could use my density to convert between grams and milliliters. Okay, so there we go. We can go back and maybe figure out how many grams of concentrated HCl we actually have. So that would be like the solution, right? This is still in the solution sense. And so maybe I kind of fall into a roadblock there. Let's maybe start going from the other direction. I'm maybe not sure what value now to use to get to grams of concentrated HCl. I have a couple different conversions up there. I see percent HCl by mass. I see molar mass as well. And so this could be a point of where, okay, maybe things are getting a little confusing. Let's look at the beginning and see if we can use any information there. And the first thing that I see is, the fact that we have a molarity. Right? So we can get to moles of pure HCl using our 2.0 molar solution. Right? So we have to do a conversion maybe to get that, but we get to moles of pure HCl. And if I think about it, now what conversion has moles in it? Well, now there's actually only one that I can shoot from, which is now looking at my molar mass. With this molar mass, I can get to grams of pure HCl. And so that would be my 36.5 grams per mole. So now we're almost there, right? We have one more arrow to fill in, and we actually only have one more conversion to actually use. So in order to get from grams of pure HCl to grams of that concentrated HCl, right, that's where I'm making my connection between the two different styles of units. Notice that we're going from this idea of pure to this notion of concentrated. And I'm going to be using this percent by mass, the 36% by mass, right? Which will be grams of HCl over grams of concentrated HCl. And now it all fits together. This is definitely a tough conversion problem. So I started from one end and went backwards, and a lot of times that works out very nicely. And then I got stuck, so that's fine. We just held off, and then we continued forward from the other side, and eventually we're able to put this all together. So we have a number of steps to actually utilize in going forward. Right? We have our first conversion to moles. Then we're going to use our molar mass to get to grams of pure HCl. Then we're going to use our mass percent to convert from the grams of pure HCl to the grams of the actual concentrated HCl solution. And now we're going to figure out the volume of that concentrated HCl solution that I need in order to make this 250 mil 2 molar HCl solution. So if I start, and we would start with already doing a conversion here. I've already converted from my 250 to 0.25 liters. This would be of the dilute HCl solution, and we would then want to use that molarity of 2.0 moles of HCl per liter of this dilute HCl solution. So that's step one, using the volume measurement to cancel to get to moles using the actual molarity. We then go to step two, which is using the molar mass that I have 36.5 grams of HCl for every mole of HCl. So my mole value is being converted to grams of the pure HCl in this step, right? So notice that we started with dilute hydrochloric acid solution with the 0.250 liters. We then converted that into pure HCl, right, as far as mole value of HCl. And now we're in grams of that HCl. We can now use the mass percent, that for every 36 grams of HCl that's in that solution, It's actually 100 grams of concentrated HCl. So notice how writing not only the units, but what the units are describing is very important here. So we're getting out of pure HCl, using that mass percent to now get into the actual mass of the solution. And this is mass of the concentrated solution. And now we're at that fourth conversion, that for every 1.18 grams of that concentrated HCl, right, there's 1 milliliter of concentrated HCl, and those are in solution, right? They're aqueous. And so that was the fourth conversion. Now getting out of the mass of the solution and getting into volume of that concentrated solution. So if we go through and do the conversion, we end up with a value of 43.1 milliliters of concentrated HCl is required. And then we could dilute that up to 250 milliliters with water, and now we have a 2 molar solution. And so that's how we can do that dilution. But we would need to measure out, that 43.1 milliliters, right? We'd have to actually figure that out, and that's definitely the harder part. So there are examples of some solution concentration units. We talked about percent by mass, percent by volume. We've talked about molarity. And there are a couple other ones out there as well. We're not going to get into too much, but other solution units that we would see is parts per million. It's actually a couple of these parts per idea. We don't tend to see these a lot. We're not going to use these too much. It's just some other units that we find. These we tend to see for extremely dilute solutions. Usually looking at environmental concentrations, water, rivers, lakes, contaminants within those aqueous systems. And so it's 1 part per million parts, essentially, or 1 part per billion parts. And so another one would be molarity. Molarity is actually moles of solute per kilogram of solvent. And it has a little value or a little symbol of little m. So we have that as well. We're not going to see that in this particular module, but going on to the second half of general chemistry, we will see molarity there. So just as an introduction for those going to that class as well. And then another one is normality. No, it's not how normal you are, but it's moles of H plus per liter of solution. And this is something that's more specific to, acid-base chemistry. Again, we don't tend to use these too often, but just so that you're aware that we do have, other units that are out there to describe solutions. Lastly, in this piece, what about using, molarity or concentration in now chemical reactions? So we talked already about chemical reactions, right? So we have a sense of, the idea of going from, mass of a molecule to moles of a molecule, and then relate that to moles of a different molecule, and then get back to mass. And we talked about that idea of like limiting reagent, theoretical yield, percent yield, et cetera, et cetera. And so this is that mole-to-mole superhighway. So, now you can do the same thing. But basically starting from volume and molarity. So just like we could use mass and molar mass to get to moles, well, now we have a new way, right? We can use volume and molarity to get to moles. So above, we would see, this idea of, grams per mole in these two last conversions, right? I'm sorry, the first and the last conversion. Now what we see in terms of concentration is something, that's similar, just a little bit different, right? That we're now starting with the volume of solution 1, right? And solution 1, right, contains our molecule, right? This is going to say contains, molecule 1. And we can do the same thing. We can get to moles of that molecule 1, now using our idea of molarity, right? Moles per liter. And then we can still use our mole-to-mole superhighway and now we can do a couple different things here. We could go to mass of molecule 2. We could go to molarity of molecule 2. So we just have a little bit more now that we can play with in terms of whether we're using grams per mole or moles per liter to have this mole-to-mole, kind of interface. So let's do an example of this. It's not too much of a stretch from what we've done prior with chemical reactions. All right, so here's our question. Right, for the reaction above, and if we look above, we have here's sodium chloride reacting with mercurous nitrate to produce sodium nitrate and mercurous chloride. For that reaction, what volume of 0.150 molar NaCl, what volume of that sodium chloride will completely react with 0.150 liters of 0.175 molar mercuric nitrate? So this is just a chemical reaction, just with the different way to get to moles, right? Because of now we're in terms of molarity. So the first step is we need a balanced reaction. And the answer right now is no, we don't have a balanced reaction. So we need to relate our molecules above, and if we do that, we see that this should be not NaNO2, I apologize, that should be NaNO3. We see a problem with the nitrates, or the NO3s. So a quick balance would say that we should have 2 sodium chlorides plus our mercurous nitrate, and that is going to produce then 2 sodium nitrates plus then our mercurous chloride solid product. So this is now balanced. And so now let's kind of look at where we need to go. Question is asking us, what volume of this 0.150 molar sodium chloride I actually need. So we can put that over off to the right. Right, we have this volume of 0.150 molar NaCl, right, that we're looking for. And where are we beginning? Well, we're beginning with our measurement, which we see here, the 0.150 liters. And so we have our other material, the mercuric nitrate. So we actually already have a volume as far as our measurement is concerned. And this is of the 0.175 molar mercurous nitrate. So this is just a mole-to-mole relationship, right? We gotta figure out moles in going forward. And so that means we could start with the mercurous nitrate, simply by using our moles per liter that we have below, right? I know the value is 0.175 moles per liter, but we can use that to figure out moles of HCl. And then we can use our value for the stoichiometry that we have above to figure out now moles of sodium chloride that's necessary. And so we see that, as a 2-to-1 ratio. Right, we have 2 moles of sodium chloride for every 1 mole of the mercurous nitrate. So that's our conversion feature there. And then we can simply use our moles per liter value of 0.150 to then do the final conversion that we have. So we have, basically 3 steps that we need to do. We need to get to moles so that we can get on to the mole-to-mole superhighway. And then finally we can do the last conversion to get to our volume. So let's start with that measurement. So we have the 0.150 liters of our aqueous mercurous nitrate. We're going to utilize the molarity, 0.175 moles of the mercurous nitrate for every liter of that solution. So that's the first step. We're getting out a volume of the solution, and we're getting into moles of the pure molecule. And now we can go to the chemical reaction to say for every 1 mole of the mercuric nitrate, I need 2 moles of sodium chloride. So that is our mole-to-mole superhighway, right? That's our conversion that we're seeing here and getting out of moles of the one starting material and getting into moles of the other. And then we're on to the third step, which is now using that molarity of the NaCl and setting it up in such a way I can now figure out the volume of the NaCl solution. And so that has now allowed us to convert all the way. And we end up with a value of 0.350 liters, right, of the NaCl solution. And so that will completely react. And so that's an example of using a chemical reaction, the balanced, chemical process, using its stoichiometry to now relate, concentrations to one another. It's really still the same idea. We're really relating molecules to molecules here. It's just a different angle to get to the mole game. We can use mass and molar mass to get to the mole game, or now we can use volume and molarity to get to the mole game.